In this problem, we are given a position versus time graph, and what we are asked to do is figure out what the velocity versus time graph is and the acceleration versus time graph is. And this is an example of erratic motion. It's erratic motion because the position of this particle is defined by more than one function. In this problem, it's defined by two functions. From 0 seconds to 30 seconds, we are told that our function that defines the position of the particle is 0.4t squared. From 30 seconds to 40 seconds, we're told that this function is linear, but we're not told what the actual function is. We just know it's some linear function that we need to figure out what it is. To work a problem like this, what we need to do is we need to look at each of the regions of the different functions individually. So we're going to be looking at what happens from 0 to 30 seconds, and then we're going to be looking at what happens from 30 to 40 seconds. And I'm just drawing these lines on the graphs to line up the 30 and the 40 seconds a little bit so my graphs look a little bit better. First, let's look at what's happening from time is between 0 and 30 seconds. And in this case, we know the position is given by the equation 0.4t squared. We also know a velocity, or an expression we have for velocity, is the derivative of our position, so ds or dx, with respect to time. So if we take the derivative of this function right here with respect to time, we get this is equal to 0.8t. So our velocity from 0 to 30 seconds is some type of straight line. And this straight line has a slope of 0.8 and a y-intercept of 0. So we're going to go from here to, let's say this is 0.8. And we can figure out what this value is. We can figure out this value by plugging in t is equal to 30. And we'll have 0.8 times 30. And this is equal to 24. Let's say we're in meters per second. So this value is 24. Now let's look at what's happening between 30 and 40 seconds. We know this is linear, and we have some information about what these points are. We know this is at 30 seconds. We know this is 40 seconds. So that's our x-axis. And we know here that this value is 360, and this value is 600. So we can figure out what the slope of this line is and the y-intercept of this line is. Let's do this. Let's from t is equal to 30 to 40 seconds. Let's say that a slope of the line we know has to be in the form of y equals mx plus b. And m is our slope, b is the y-intercept. So we could figure out our slope. Our slope, m, is equal to y2 minus y1 divided by x2 minus x1. So this is going to be equal to 600 minus 360 divided by 40 minus 30. So let's calculate that. This is 600 minus 360 divided by 10. And we get this is equal to 24. So our slope m is equal to 24. Now we got to figure out what our y-intercept is. To do this, we have a slope of 24, and we're going to have to pick one of these points, either 30, 360, or 40, 600, to figure out what our y-intercept is. I'm going to just pick 40 and 600. So what I have is y is equal to 600, which is equal to our slope 24 times x. In this case, let me be careful. This x is really my t term. This is really a t term. And this y is really a s term. So just being a little careful. So t is, what did I say? I wanted to pick the 4600. So this is going to be 40 plus b. Okay, let's solve for b. We'll have 600 minus 24 times 40. And that's equal to minus 360. So here, b is equal to minus 360. And that means the slope of this line the equation of this line is equal to whatever our value of s is equal to 24 times time minus 360. And if we had chosen the other point, that would be fine. So we'd have 360 minus 24 times 30. And again, we would get that this is equal to minus 360. So it doesn't matter at which point we chose because it's a linear line. So that's the slope of this linear line. And we're going to do the same thing. We're going to say, okay, if that's the slope of the line, that's the function of my distance from that defines the position of my particle from 30 to 40 seconds, then my velocity is going to be equal to the derivative of s with respect to t, and then this is going to be equal to 24. And that works out. We start at 24 right here, and then we just have a constant velocity of 24, and this will be, we'll say it's meters per second. So we figured out what our velocity graph is. Now let's look at the acceleration graph. In the acceleration graph, we do the same thing. For our acceleration, we know that our acceleration is equal to the change in velocity over the change in time. We know our velocity, and this is going to be from 0 to 30 seconds. Our change in velocity is this 0.8 t. So it's 0.8 t over dt, and this is 0.8. So our acceleration is constant. Our acceleration is constant at 0.8 meters per second squared. And then we want to look at what's happening from 30 to 40 seconds. And our velocity in this term, well, our acceleration is still dv dt, and our velocity is 24. So 24, the derivative of 24 with respect to time, and this is just equal to 0. So we have no acceleration from 30 to 40 seconds. It's equal to 0. Now, this is my acceleration graph. And all I want to do now is just sort of talk about and check my work. If we think about this, to go from position to velocity, I take a derivative, and velocity to acceleration, I take a derivative. So that means if I go from acceleration to velocity, I should only have to take an integral. And let's check to see what my velocity is if this all works out right. What my acceleration is saying is that the area under this curve is going to give me my velocity at that point. So if I look at that, if I take the area under the curve from 0 seconds, which is over here, to 30 seconds, which is over here, I am going to get whatever my velocity is at that point. And in general terms, this is an easy shape to do. I can say, all right, the area of this curve, under this curve right here is a rectangle. I can say 0. And I'm just going to say this is my check. 0.8 times 30, and this gives me 24 meters per second, and that's what I thought I should get. I could also say this more formally, that since my area, or my acceleration, is my change in velocity over the change in time, and my acceleration is 0.8, I can figure out what this acceleration at 24 meters per second is. And this acceleration is going to be the integral from some dt is equal to dv. And I need to figure out the bounds of integration. So I want to go from 0 seconds to 30 seconds. And I want to go from a velocity, I start at 0, and I go to some unknown velocity. That's what I want to figure out. So now, if I integrate this, I get 0.8t, which is evaluated from 30 to 0, is equal to v, which is evaluated from v to 0. Okay, again, I'll have, this is 0.8 times 30, which is equal to 24, and that's equal to v. So I get the same answer, and this rectangle is just this integral solved. I can do the same thing with this triangle right here. I can say that the function of my line right here is 0.8t. And what is this point right here? I should get 360. So 0.8t dt is equal to ds, right? V is equal to ds dt. So if I take the integral again from 0 to 30, and this goes from 0 to some distance s, I'll have this is 0.8 t squared over 2 evaluated from 30 to 0 is equal to s evaluated from s to 0. All right, the only term that matters is 30 because 0 just goes away. And what I'll have is 0.8 times 30 squared is equal to 720 divided by 2, and that gives me 360. So I could check all the points this way just to make sure that I didn't make any type of mistake with my calculus. But now I've graphed from a position time graph, I've graphed my velocity versus time and my acceleration versus time graphs.